Hello everyone, my name is Ileana and today I'll be presenting the article An Interactive Exploration of the Societal Impacts of Inorganic Chemistry, a base metal view on sustainable catalysis. It appeared in the Journal of Chemical Education in 2025, so pretty recent, and this paper is written by researchers from several Canadian universities, and it focuses on how to teach sustainability in inorganic chemistry, specifically by turning a conference session into a set of hands-on interactive activities. Before diving in, we'll do two quick definitions because they'll be used a lot in this article. So base metals are inexpensive metals like iron, cobalt, and earth abundant, so they're available, like iron, cobalt, nickel, and manganese. And then sustainability is balancing efficiency, cost, environmental impact, safety, and social responsibility in chemical processes. So the goal of this paper is to create and test interactive, game-based activities that help chemists better understand sustainability and catalysis while also building community. So we're going to start. First, we're going to talk about figure 1. That is before the actual results of the experiment. This is figure 1. Before the activities, the paper presents figure 1, which maps out the entire structure of the symposium, what's going to happen. Here's what figure 1 shows: yellow boxes, broad learning objectives, things like understanding sustainability at a global level. The blue boxes are specific chemistry objectives. The pink boxes are conversation-based activities used early on to get participants talking. And the green boxes are hands-on activities, arranged from light green to dark green, light being easier, dark being more complex. So figure 1 works like a roadmap. It tells you here's where we're starting, here's where we're going, and here's how hard it gets along the way. It's basically the conference version of the video game level map, except instead of defeating a boss, you're defeating your confusion about sustainability metrics. So now we're going to get into the results. There was 5 major activities included, so we're just going to explain and go through each one. Activity 1 was defining sustainability. This has to do with figure 2, which is this one. What the activity was that the participants defined sustainability and placed their definitions into a 3-circle Venn diagram, that is right here, representing society, chemistry, and base metal catalysis. Figure 2 displays the completed Venn diagram with a cloud of participant responses written on sticky notes placed inside or between the circles. The figure shows most definitions sit between society and chemistry, which is renewable and ethical, reduced waste. That's what chemistry. But very few land in the base metal catalysis circle, meaning chemists rarely think of sustainability in specific inorganic terms at first. Pretty much people think broadly about sustainability, not chemically. So this activity helps establish the need for more technical discussions later. The second activity was life cycle analysis, and that has to do figure 3. This is figure 3, and table 1. This is table 1. So what the activity was was participants compared catalytic routes to make, bear with me on this, N-cyclohexylmethyl aniline using LCA categories such as global warming potential, human toxicity, atom economy, E factor, and figure 3. Let's go back to that one. Shows puzzle pieces representing each LCA category. Down there. Each puzzle piece corresponds to a sustainability metric, and participants had to assemble them to evaluate different catalytic pathways. It's visually designed so participants can hold sustainability categories in their hands, literally. And then table 1, this is table 1, provides a color-coded chart comparing the 2 catalytic routes across all the LCA metrics we talked about. For example, one route scores better in global warming potential, another scores better in toxicity. Neither route is perfect. So pretty much this tells us that sustainability isn't one-dimensional. Depending on which metric you value most, your choice of best catalyst can change. Activity 3, this is figure 4 and 5. So this is figure 4 right here. And this is figure 5. So you know what I'm talking about. Participants built their activity, they built a Jenga-style block tower, which with each block representing a catalytic design choice: metal, ligand, solvent, safety, sustainability factors. So pretty much the thing was greener choices equals stable blocks. Risky or unsustainable choices were weirdly shaped or unstable blocks. So figure 4 is a photo of the assemble. This is the tower. I'm trying to find it. Yeah. Oh. That was figure 5. The tower visualizes how different choices stack together, quite literally. And then figure 5, this shows one of the worksheet prompt pages used by participants. I think I might have switched those, reversed those as figure 4. And the sheet asks questions like, what ligand would you choose? What compromises does this choice create? It guides participants through thinking critically about each piece of the tower. Pretty much the takeaway is that catalyst design is a balancing act. Improving sustainability in one area can destabilize another part of the system. Then we have activity 4, which is designing CO2 reduction catalysts. Participants designed hypothetical CO2 to form a catalyst by choosing a metal and then a ligand scaffold, a mechanistic pathway, sustainability priorities. This shows the CO2 catalytic cycle with arrows showing electron flow and how CO2 transforms into formate. The catalytic cycle steps include CO2 binding, hydride transfer, protonation, product release. This figure helped participants visualize the mechanism so they could design a catalyst consistent with it. The activity ties the chemistry mechanistically to sustainability, helping chemists integrate electronic structure, ligand effects, and environmental priorities. And then there was activity 5, which is the escape room. Participants created an online escape room reviewing sustainability concepts. Several participants loved this format, but some puzzles have too many acceptable answers. So pretty much this takeaway is that gamification boosts engagement, but clarity matters. So for the discussion, the authors conclude that active learning increases engagement compared to typical conference talks. Participants felt more confident discussing sustainability topics. Collaboration across career stages became natural. The activities also built a sense of belonging, which is strongly linked to persistence in STEM fields. They emphasized that these activities can be transplanted directly into undergraduate inorganic chemistry classes. So analysis of this is the strengths: very innovative teaching approach, embodies real-world catalytic decision-making, encourages collaboration and communication, highly relevant to the future of inorganic chemistry. And limitations: there's no quantitative data on learning gains. Some activities were too advanced for new chemists. The escape room answers, as we talked about, were ambiguous, and it's hard to scale beyond small groups. But overall, a creative and genuinely useful model for teaching sustainability in inorganic chemistry. To wrap up, this paper presents a unique approach to teaching sustainability using activities that combine chemistry, society, and hands-on problem solving. Each figure from the Venn diagram relates to the LCA puzzle pieces to the catalyst tower. Helps participants understand sustainability in physical, visual, and interactive way. Thank you.